record so that I can save this for other classes. Welcome to data management, just a quick overview of what we've done so far, everything from correlation to interpolation, extrapolation, outliers, and influential points. So I'm going to start by going back to one of the main slideshows that we looked at. This is an important one to go through and to review before the quizzes. And hopefully that helps with a bit of an overview here. So how to do a correlation, and this is the main part of this unit, is to start by making a scatter plot, which we've done. You have to have the scatter plot and line of best fit, and that really becomes the key for the R value and then interpolation, extrapolation too. So this is one of my favorite examples, because before this, if I gave you temperature and ice cream sales, all you could do was mean, median, mode, range, standard deviation. You could get the scatter plot, you could get the line of best fit, but we had no concept as to how good that was or the strength of it. And now we do, because using an R value, you can now see that there's a very strong relationship between temperature and the money here. And I want you just to take a minute to appreciate how powerful this correlation is. It does not matter if you're dealing with numbers in the hundreds or billions of dollars. It does not matter if you're dealing with decimals. It does not matter if these numbers are related. The R value always works. And it gives you a number close to zero if there isn't a relationship, if they're all scattered, or it gives you a number close to one if it's a near perfect positive, or to -1 if it's a negative perfect correlation. And that just amazes me that regardless of the data, that's what's happening. Once we have the line of best fit and the equation of that line, which you get in Excel by just clicking on the equation option, you can now interpolate and extrapolate. These are fancy words for doing what you did in grade 10 math. You take any X value, you sub it into your equation, solve for Y, and you get the Y value. That's it. So that's all interpolation and extrapolation is using the equation of the line of best fit to sub in an X value and solve for the Y value. Both are predictions, so they are the same because they're predictions. For example, if I'm selling ice cream and it's going to be 21 degrees that day, this predicts for me that I will have $480 worth of sales based on the trend of the previous data. Extrapolation is the exact same thing, same equation, but it's a value in the future. So it's a higher value, something that's outside of our data set. So here we have 29 degrees going into the equation. That's the X value. Solve it on your calculator to get a Y value of 750. One of the most common true-false questions I'll put on a quiz would be interpolation is more accurate than extrapolation. And it's true. That's a true statement. Extrapolation assumes that the relationship will hit linear, but of course, if you hit a point where it's 30, 35 degrees, people aren't going to go outside to parks to buy ice cream anyhow. So eventually this curve will level off and go down. The rest of this, we're going to use technology for. This is an incredibly complex formula that gives a very simple number between -1 and 1. You will just use equal to Corel on the spreadsheet. And then once you use this, equal to Corel, highlight the first data set, highlight the second data set. You have all these different options here that help us describe whether it's a strong relationship, random, weak relationship, etc. And this you just need to memorize. You just need to know that 1 is perfect. Anytime you're above 0.67, that's going to be a strong relationship. From 0 to 0.33 will be a weak relationship, and it continues on from there. So I like this picture because it just gives an overview of how scattered it looks as the relationship becomes weaker. Going through the rest of this, we can use it for predictions. There's a lot of other information that we can go through here. I'm going to come back to nonlinear next week, so I don't want you to get confused with that at all. The key is just using the equation of the line of best fit so that you can interpolate the data, extrapolate the data, that kind of thing. Okay, so I'm going to stop with that slideshow and just see if there's any questions. So at this point, if there's any questions, unmute your mic and ask me, or if you want to put a comment in the group chat. I'm assuming by the lack of comments that people can actually hear and that things are working here. So hopefully that helps you with correlation, the strength of the correlation, and also interpolation and extrapolation, just using that equation. Okay, I'm gonna share then the other portion that we looked at yesterday, and hopefully this will help with the idea of the strength or weakness when it comes to looking at a scatter plot. So outliers and influential points that we have here. Let me just go and share this slideshow. Outliers and influential points are very similar. They're both data that's outside of the main data set, underneath the umbrella term of outliers. Influential points is just a specific kind of outlier. The key is that they both impact the R value, but an outlier, a traditional outlier that I'll show in a second, tends to lower the R value, so it makes it weaker. An influential point is almost worse in that it actually makes it look like you have a pretty strong relationship where you probably don't. And that's best done through pictures here. So this is your classic outlier effect that lowers the R value. So this graph, as horrible as it is, would have an R value of about 0.3. So it would be a weak relationship. But if you just look at these 7 data points, they actually follow the trend line fairly closely. It's this one that's impacting it. So if you were to remove this point from the data set and do equal to Correll just with years and frequency, you would actually get probably a moderate relationship. So this is the example of an outlier that decreases the R value and makes the relationship look weaker than it is. I think this makes sense. We have every single dot is actually a person that has 2 values. So Jane is a person who has studied for 10 hours and got a mark of 70. And it's important to remember that every single dot just represents a person with 2 different data points, X and Y, that they're linked to. These I'm gonna skip through because I think it's pretty straightforward. A random correlation is just when the data is scattered. We would not call this a weak correlation, even though it's in that range. We could call it a very weak correlation. We could call it near random correlation, but this clearly has no trend line that can be put onto it. What I want to emphasize here is that you are only going to use Excel for this. I find R value absolutely fascinating, how you can put any kind of data into it, and really it becomes an index where using square roots and averaging, it boils it down to a very simple number between -1 and 1. But you will never be required to reproduce this by hand. What I need you to be able to do is take the R value and be able to interpret it as to whether it's positive, negative, strong, moderate, weak, perfect, and whether it's a linear or a nonlinear correlation. To end here, there are 4 major cautions when using correlation. I love correlation. It's my favorite stat. I use it in my own work when looking at a relationship between different data sets. I'll look at a relationship between your homework marks and your online EdSpeak quiz remarks to see what's happening there. And anytime I get a weak relationship, it tells me that a homework assignment you did had almost no beneficial impact. Whereas if there's a strong relationship, then it shows that it does. So as much as I love correlations, there are 4 major cautions to deal with. One is that you cannot get a linear R value. So using that equal to Correll, it will not work with a non-linear graph. So in this case, if I was to do a correlation here, I would actually put a linear line of best fit on it, a straight line. It would actually be horizontal. My R value would be very weak. But clearly this is not a weak relationship. The data closely follows the curve. So this is what we'll look at in the future. It's called a strong nonlinear. In this case, it's parabolic or a parabola relationship. So we'll come back to these. Those that are looking ahead on the spreadsheet will see that there's an R squared button. That is for nonlinear curves, and it works very well for that. But the equal to corral is for the straight line, linear line of best fit. The other cautions, depending on your data set, you can't just look at a small part of it. So if I only went and did a scatter plot of those that are 6 years old, it would look like a weak relationship. I wouldn't get a trend there. But going from age 3 to 9, I get a strong relationship. And the same thing happens if you only look at the top part of your data. So that's another caution with correlations. You can't limit it. So I shouldn't do a big correlation study just looking at 17, 18-year-old students in our class. It would be better to go and look throughout the entire high school age range. This really strange looking graph here is the weirdest and best example of influential point. If you removed the top influential point, that's clearly an outlier, this data here looks like it's almost random. At best, I would say it's positive weak, probably around an R value of 0.10 or so, because there's just a little bit of a trend that's visible here. If you actually put this entire thing into a spreadsheet and did equal to corral, you would actually get an R value of probably 0.35 to 0.4. That one influential point way out there actually goes and tricks the R value, so to speak, into making it look stronger than it is. Anytime you have an influential point or an outlier, do what I had you do on the earlier spreadsheet where we looked at the hockey data, where you remove that grade 9 player who has an incredible points in that hockey tournament. So remove him, look at the R value with him and without him so that you can make a decision. And the final caution, and we will definitely deal with this in our class too, when I have you doing your own correlation studies and you're collecting data from people in our class, you cannot just study 5 people in our class. So bare minimum of 20. This is a completely useless study to go and pick 6 people that go and show the trend. In reality, we know from our class that there's people that study hard that get lower marks, and there's people that barely study that get higher marks. So you would never have a perfect relationship like this. But you can manipulate data by just showing a small part of the sample size. So hopefully that gives you a bit of a verbal heads up as to how these different things relate. Now your key is to go on and actually do a bunch of spreadsheet work. So you have a fascinating data set, in my opinion, that looks at an older grade 12 class I had. It was a grade 12 class where a lot of students lived far from the school, so they had long bus rides. They did not like math. There were some very poor marks, and they were so heavily addicted to smoking. And so students with, smoking multiple packs of cigarettes a week, and just a fascinating data set to be able to look at the relationship. So as a teacher, I ask questions like, does a long bus ride make my students do more poorly in math? And I think what stands out to me with that class that's different than yours is that it was also a period 1 math class. And most of my tests, of course, would happen at the beginning of the class. So if you were on a long bus ride and your bus was late, that impacted how much the test you could write. But even more so, if you're heavily addicted to smoking and have just been on a bus for an hour and a half, you're going to have a couple of smokes before coming into math class and likely be 15, 20 minutes late, missing, a good part of the test too. So any questions before I sign off here? Otherwise, I will try to end the recording here.